Let me introduce our work on orchestrated container migration and handover in mobile edge computing. And this work is done by me, Mao, and Professor Lotier, Hill, and Professor Tony Quet. Let me introduce the motivation. Mobile users are ubiquitous and demand more and more computational resource. So thus uploading to the cloud is the solution. However, to save battery life and to reduce end-to-end delay result in improving user experience. So thus, uploading to the cloud is not a solution. Instead of that, we upload computationally intensive tasks from mobile user to the virtualized environment such as Docker container run on the nearby edge servers, which is the mobile edge computing nowadays a solution. However, the user are mobile, so we need to migrate running container to a closer server. And also we need to hand over the wireless connection from the old base station to the new base station. And we address joint problem of container migration and base station handover. And we aim to answer the question in how to migrate container fast over the wide area network and minimize the service interruption. With that, we will propose a mechanism on the hierarchical edge computing architecture. Can include the many hidden edge layer, but in this figure, I plot only 3. And the mobile user can upload the service on the Docker container used run on the edge server that's co-located on the base station. And when the user are moving to a new base station, the wireless connection have to hand over to the new base station, and also the migration service can migrate the Docker container DU to a new edge server. Docker container have to be exactly the same memory state to keep the stateful application up and running in the same state for the mobile user. And when the user are moving to rural area or somewhere far away from the center, the service can upload to the edge layer 2, which covers several many other base stations. And with the same mechanism, in case it's moving to the far rural areas, it can forward to the cloud computing. And with this part, we can cover many other scenarios in any path we can jump. And in order to do that, we implement the central controller with the several modules, deployment module, monitoring module, and a centralized database to have a fully observe of the full network. And the heart of the central controller is planner to do the migration and handover. So that's the hierarchical edge computing with our framework, our mechanism can automatically deploy, manage, migrate, recover, upload the service for mobile user. So we will look at the mechanism in the planner to do migration and handover jointly. In thus, we propose an orchestrated container migration and base station handover mechanism, including 2 parts. Part A, optimal placement, which determine the best destination of edge server for migration and the best base station for handover. Aim to answer the question is where to migrate and handover. So in the part B is timing. So in this part, we aim to answer the question is when to do the above 2 tasks, which determine the coordinated timing to trigger various stages of migration and handover processes. And let me introduce the part A, our optimal placement. First, we need to estimate the chain end-to-end delays because we care about the end-to-end delays, which these use BS is user use connect to the base station B and associated with the service in the server S can be decomposed in 4 parts: processing delay, transmission delay, propagation delay, and queuing delays. And we are interested in the chain of end-to-end delay when we make the decision of moving from base station B to B price, migrate the service from server S to S price, which can estimate in this formula. And all this kind of estimation can be estimated by heuristic number. With the chain end-to-end delays, we can obtain the gain from the migration. Can be calculated in the total gain for all users when migration from server S to S price and handover from base station B to B price. And at the Z is the indicator number to indicate the association between the user to the base station and the service run on the server at the time t, and we interested in the estimation on the future time t price. And with us, we can, because time t, we can know based on the current status. So we find the variable on the z on the time t price in the future. And the cost or decision of migration and handover is calculated based on the downtime. During the migration and handover, the service is up, so we measure the downtime. And the cost is the total downtime. Our objective is to maximize total profits and defined by maximize the gain minus the cost. We have a several condition in the domain, and user only associated with one base station and use the service on one server, and the resource constraint on resource on the memory, network, CPU, and the constraint on the network coverage. Total number allowed to serve on the one base station. We formulate and use open source corn and branch code to solve the integer linear programming to find a numerical result to find the z. And then we propose a part B of the mechanism, which is timing, which determine the coordinated time to trigger various stages of migration and handover processes. And we answer the question how to migrate running container efficiently by proposed delta checkpoint technique. Then we trigger when to trigger various stages of migration and handover in this part. First one is the delta checkpoint technique. We use Docker container for containerization uploaded service because it's widely used nowadays in industry. And the delta checkpoint technique consists of two phases, the pre-migration phase and migration phase. The pre-migration phase, we checkpoint the container and leave the container running so that the service is still up and run. And in background, we transfer the whole memory state to destination server. In the end of pre-migration, we can do the final migration. We checkpoint and stop the upload service, and then transfer the delta memory stage, which is the difference between the final checkpoint and the pre-migration checkpoint. So the delta memory stage will be much smaller than the whole checkpoint to the server destination. So in the destination, we reconstruct the final checkpoint and restore the Docker container. Now we see how we find the downtime for the migration and handover. In this figure, we see the several options of handover and migration. The first timeline is the container migration. The first and the second option of handover is associated with the early or too late handover, which resulting in high downtimes for the service. In the last option, in which the best trigger time is associated with the smallest minimal total service downtime, which we should hand over during this time window. And with that, we can estimate backtrack to the time to do the handover, time to trigger the migration, time to trigger the pre-migration based on this estimation. With that, we see the experimental setup. We have built 3 uploaded services using the real-world scenario, real-world application, and deploy in the Docker container. The first simple service is just TCP dump server, and the second service is OpenFace, which is the face recognition service. The third one is the YOLO service, is object recognition service, only implemented on CPUs in order to make the migration. All the services are stateful application, which means it helps maintain the state information of user context for future session. Such a video game, we need to keep the video state at the same before and after we hand over and migration to the new base station and server. And we evaluate 3 services on 4 planner. The first one is cloud planner, which is a tradition and no migration. The service always run on the cloud, only handover based on RSSI. The random planner, we can migrate to random server and plus the handover based on RSSI. the nearest planner is always migrate to the nearest server and hand over based on SSI base. And the fourth planner is our orchestrated planner. In this one, we trigger handover and migration coordinatedly to obtain the best destination at. We set up the scenario like this. We built 3 edge servers in this kind of computer, and the central cloud at the dev box. You deploy on the edge. And we also build a simulated environment to make the experiment reproducible. So the mobile is moving in the direction line in the corridor. And we emulate the wide area network among the edge server in this kind of number. The bandwidth and latency is quite slow. Yeah, among the edge server and cloud is also low bandwidth and high latency. The experimental results showed in this one. We first look at the end-to-end delays. The simple service just reflect the network configuration. And for OpenFace and YOLO service, we can see the processing delays of the cloud is smaller than the edge server because it's more powerful, but the transmission delay is higher. And our orchestrated planner is always the best because it's can reduce significantly. So for example, the YOLO service, we can reduce random planner by 22% and nearest planner by 12%. So we zoom into a 50-second elapsed time during which it happened handover and migration. For the cloud planner, we don't see any migration and only the handover observed here. And for random planner, and also nearest planner, we observe 2 gaps. The first gap is handover, the second gap is migration. Our orchestrated planner, we can see only handover and migration happen at the same duration. So that we can minimize the downtime and incur less fluctuation in between. And we can achieve the best transmission delay after we make the decision of migration. Next, we see at the total service downtime. We see the service downtime increase when we increase the service complexity. So we can see the orchestrated planner reduce the service downtime of the random and the nearest planner by 30 to 40% for all 3 services. And with our denser checkpoint technique, we can make the comparison of the checkpoint file size. The first, the image size, we assume the service is already in the edge server, or we can do pre-fetching when the service is running. For the pre-migration and the final migration, we can see with our denser checkpoint technique, we can reduce the final migration checkpoint size is only 0.4 to 4% of the data transmission between the source and destination edge server, resulting in reducing total service downtime. So our denser checkpoint technique can reduce data transmission significantly. With that, I will conclude the presentation. So we presented a hierarchical edge computing to address the joint challenge of container migration and base station handover. And we propose an orchestrated container migration and base station handover mechanism by proposing 2 parts. Part A is optimal placement and part B orchestrated timing. So that we can jointly minimize the end-to-end delays and total service downtime. We also propose a denser checkpoint technique to reduce the memory state to transfer in the final migration. Finally, we implemented the orchestrated planners and other planner on real testbeds and evaluated using the real world application, YOLO and face recognition, OpenFace, and experimental results showed the proposed mechanism outperform others by significantly reduced end-to-end delays and the service downtime for mobile users. With that, I will conclude the paper. For more information, please refer our paper or contact me, Mao, if you have further question. And Thank you very much for your attention.